Okay, welcome back. Let's take a look at the other part of VAAI, the part of VAAI that takes care of array thin provisioning. Basically, with an array thin provisioning APIs, what can happen is a host can integrate with a physical storage to determine and detect the space that's used within thin provision LUNs. So if you have a LUN on your storage that's being presented to vSphere as a thin LUN, say for instance, the LUN is a 2 terabyte LUN, and it's being presented to vSphere as a 2 terabyte LUN, but it's a thin LUN. So what if vSphere is actually only allocating maybe 1 terabyte of space, right? It's got enough virtual disks in there that it's actually only consuming 1 terabyte of storage. Well, the ESX server is going to see that as 2 terabytes normally, even though it's really only using and consuming 1 terabyte of storage. With the thin provisioning integration, the host can perform the following tasks. It can monitor the use of space on the thin provision LUNs to avoid running out of physical space, and the host can inform the array about data store space that's been freed when the following actions occur. This is actually one of the interesting aspects when thin provision storage is used, is that whenever virtual disks and VM files are deleted from the data store, or when virtual disks are migrated off of the data store and moved to another data store, or whenever snapshots are deleted and consolidated, normally without this thin disk provisioning integration, that space doesn't actually get reclaimed automatically at the backend storage side of things. Right? Think of layers of a virtualization, or I should say all of these different layers of storage of abstraction occur when you have all these different layers of virtualization. In fact, some of these aren't really related to virtualization so much, in that if you were to have a storage array that's filled with a whole lot of different types of disks that get organized logically into a logical unit built on top of RAID, for instance, that LUN then gets partitioned to then be formatted with VMFS. The VMFS file system would then have virtual disk placed upon that, which then the virtual disk would then be partitioned by the guest operating system to be formatted with the guest OS's file system. So a lot of different layers here, right? With actually quite a few different file system formats and layers and so on. The thing here is that if a file gets deleted at the top level, at a higher level, it may not automatically get deleted at a lower level. This is even more prevalent when you think about big files like virtual disks that might be hundreds of gigabytes in size, right? If you delete a file from the VMFS, will that automatically get the space reclaimed at a lower level? With thin LUN provisioning, that doesn't happen automatically. Basically, data gets deleted within the guest OS, or data might get deleted in the guest OS. If that was a thin virtual disk, would that be something that we could reclaim at the virtual disk level? If a virtual disk file is deleted from the data store, would that be deleted by underlying storage? In either case, the space in the array would not necessarily be freed. This is what we refer to as dead space. So here we have an example. We've got a set of virtual machines, virtual disk files. They're all 100 gigabytes. And so we decided to delete 3 of these VMs, right? So that's roughly 300 gigabytes of storage. That if I were to delete the virtual disks, that would then remove the virtual disks from the VMFS data store. So the VMFS would assume the disks have been freed up with these extra 300 gigs of disk space. But if without the underlying storage being aware of the fact that those 300 gigs have been freed, you now have essentially 300 gigabytes of dead space at the LUN level, which can't be used for other things. Basically what needs to happen is what's a special system call called a SCSI unmap command that would need to be sent from the higher storage level to the lower storage level. That frees up the space for us. Now, the unmap command is something that has been supported in VMFS. It just was not automated up until VMFS version 6. So basically, there's different ways to reclaim space in a VMFS environment. You can do what's called a manual space reclamation, where you actually run a command on the ESX server's command line, or you can have an automated unmap command that is done through the file system. So as we see on our table here, automatic space reclamation is a feature unique to VMFS 6, whereas manual space reclamation using the ESX CLI command is something that has been available in both VMFS 5 and VMFS 6. So basically with VMFS 5, what customers would do would actually schedule the ESX CLI command to run off peak hours, right? That's actually one of the things about why this wasn't necessarily automated all the time, is because what the unmap command has to do is has to search out for files that have been marked for deletion to then inform the underlying storage layer about the file blocks that can actually get deleted off of the underlying layer. And that in itself can cause a fair amount of disk I/O, especially if it's done throughout the production day. So if you do this off peak hours, this is the best practice for the manual disk unmap operation. Let's take a look at what this syntax looks like. The ESXCLI unmap command is basically this syntax. You'd run ESXCLI storage VMFS unmap, provide the appropriate options. -L is the easiest, that you just simply provide your actual data store name. Or you could add -U and use the volume UUID instead. But, go ahead and use the data store name. And then, but you have to use one or the other. You can't use both. But the another important thing is you don't have to, but the -N option specifies the number of VMFS blocks to be unmapped in this iteration. It by default will unmap 200 blocks, right? 200 1 megabyte blocks in one iteration. So you typically would script this to check to see, well, how many files were actually marked for deletion so that we can determine how many times we need to run this unmap command. If you want to specify a different number of blocks in the iteration, that's one other option, but generally you'll just run it with the 200 block option so that you can run it and then run it again and run it again until the files are properly been removed by the underlying storage. However, VMFS 6, this is now automated. Basically, when you create a VMFS 6 data store, you've seen this probably as you go through the wizard, there is a question here that will ask you a couple questions, right? It's going to ask you whether your file system is going to be comprising of the entire LUN's capacity, which it should be, but it will also ask you for the block size and the space reclamation granularity level. Well, the important thing is in order to have the reclamation to be automated, both the block size and the space reclamation granularity size need to be the same. So they are actually both 1 megabyte by default. And in fact, in the VMFS wizard here, you can only set this to 1 megabyte. So there really isn't anything you're going to set this to other than 1 megabyte. But if the underlying storage actually had a different reclamation granularity size, this would be a problem. And then you'd have to do the whole unmap in a manual process. But if they're the same, which they should be by normal default settings, the next step is what's your space reclamation priority? It is by default set to low priority. If you look at that slider though, that slider actually looks like it has a wide area of things to choose from. There's really just two options. There's low priority over on the right-hand side and then disabled on the left-hand side. So if you had space reclamation priority set to disabled, well then it won't do it. You'll have to do a manual reclamation using ESXCLI. If you have it set to low priority, you can then assume it's going to go ahead and do this. And what it's going to do, instead of setting it to X number of blocks per iteration, what it's going to do, it's going to do this on a periodic point throughout the day, trying to average the reclaim rate to be no more than roughly 25 megabytes per second. So that's good. It doesn't want to induce a huge load on your environment here by causing all these unmap operations. But that's an adjustable setting. Now, while there actually is a medium setting and there's a high setting, those are only available from the ESXCLI command line again. But actually another more even appropriate option is that once you've created the data store, after hitting OK here, go into the data store settings page, right? Click on your data store, go to the configure tab, and then over on its main panel, you'll see a space reclamation section. Hit edit and you'll find there is already set that it's, well, I should say, if you look at the main panel, it says it's already set for low priority. But if you select edit, you can then choose, instead of choosing, say, medium or high, instead just actually choose the actual reclamation rate that fits your environment's most appropriate. Now you'll notice the smallest it can set to is 100 megabytes per second, and you could set it to maybe as high as 2000 megabytes per second. This is looking for reclaim opportunities, and that could produce a lot of I/O overhead. So you just want to be careful here, but you have some control instead of just leaving it at the low setting, which is, the default setting. But if you want to change the rate, maybe you're actually finding the environment has a pretty volatile environment where files are getting deleted all the time. I mean, think, when would you ever need to change this? You've got an environment where files get deleted frequently, that you're needing to get space reclaimed all the time. That may not be something that happens very frequently in a lot of organizations. Thereby leaving it with a low priority is a good default setting. So what about in the guest OS? If the guest OS is recognizing that it's been presented with a thin disk, well then, what if the guest knows it's deleting files that it should be able to send unmap commands from the guest to the virtual disk, which then lets us actually reclaim the space in the virtual disk at lower storage levels. That's a pretty cool trick. This has been available in Windows environments since the Windows Server 2012 R2 release, and it'll send unmap commands for any thin virtual disks that Windows recognizes that is running in a thin virtual disk. You just need to make sure it's enabled depending on what version of VMFS you've got. If you got VMFS 5, this actually is not enabled by default. You'd have to set this in your ESX servers so that they're supporting this feature. If it's VMFS 6, as long as you have automated reclamation set in the VMFS version 6, you're set. So for those VMFS 5 environments, what you'll need to do, find this parameter on your ESX server's advanced settings. It's called VMFS 3 enable block delete. This is normally set to 0, which basically says that the guest is not able to delete file blocks, right? If you set this to 1, now the guest can actually send the unmap commands, and then we can actually see that at the thin disk level and then basically shrink down the disk as files are deleted from within the guest. Now, there are some prerequisites, right? The virtual disk does need to be thin provisioned. The guest host must be able to identify that the virtual disk is thin provisioned. So certain versions of Windows and Linux, for example. Your VM hardware does need to be version 11, which is basically vSphere 6 or later. And the enable block delete advanced ESX host setting must be set to 1. But that's if you have VMFS 5. If it's VMFS 6, on the other hand, well, all you need to make sure is that the VMFS 6 space reclamation priority has already been set to enable, right? Basically low priority, and it's all automatic. And then again, as long as the space reclamation interval or the space reclamation granularity setting is a multiple of 1 megabyte, that's another prerequisite. Also, for VMs with snapshots in the default space efficient format, the VMFS supports automatic space reclamation on hosts with vSphere 6, 7, and later. So that's pretty cool too, that if the file is actually being shrunken down because it's an SE space format file, it can also get that reclaimed too at the lower levels. So that pretty much sums up our API for array integration. We do have a quick question here for those of you, again, following along. Which actions apply to ESXi hosts that use storage devices where the storage APIs are leveraging storage array integration, right? So which of the ones here are all part of this API called vAAI? Does vAAI inform the storage array that it can reclaim free space? Yeah, we actually just talked about that. Can vAAI offload certain storage operations such as offline cloning to a NAS? Well, yeah, it sure can. Can vAAI retrieve information about its storage array such as its storage topology and capabilities? We haven't talked about that yet, so no, that's actually not part of this. And can vAAI offload special or specific storage operations to a block storage device, such as Fiber Channel and iSCSI? Oh yeah, it sure can, right? The hardware acceleration is a big part of vAAI. So basically 3 out of the 4 answers apply to this. So again, that ends our lesson on the vAAI set of APIs, where we described how the API's array integration helps work with offloading our storage operations as well as with thin provisioning supports. And we also showed how space reclamation works with VMFS data stores. So we'll take a quick break and we'll carry on with the next lesson. We'll see you in the next one.